Okay. Hey, welcome to another Origin seminar this week. Today we have a talk from Yifan Zhou, who's actually did his PhD here at U of A, and Dr. Daniel Pai will introduce Yifan.
Yes, welcome Yifan. It's a real pleasure to have Yifan back. He's one of our own, has been doing a PhD here, and I think you got your PhD in 2019, right?
Yep.
I had the pleasure to work with Yifan. He has done, and many of you know Yifan already, he has done really exciting and very high-profile work on studying rotational modulations, high contrast situations, measuring the day on directly imaged exoplanets and planetary mass objects. He has also been doing very exciting work, and that's what he will be talking about today, on measuring directly accretion to protoplanets in disks. That's a parallel research direction. After finishing his PhD at Stewart Observatory, he moved to the University of Texas, Austin, first with the McDonald Fellowship, and then a year later with the 51 Pegasi-B Fellowship. Also, these are very prestigious postdoctoral fellowships. And Yifan is leading multiple Hubble and soon James Webb programs too. So it will be very exciting to hear what he has to say about this research. So I would also mention that there is Serena circulated a Google document, so you can sign up and grab a spot in Yifan's schedule. So Yifan, take it away.
Great. Yeah, it's great to come back here after. Yeah, it's so difficult during the COVID time and I don't remember like how long I have been left, but it's like 2019 and it's more than 3 years, and it's such a great pleasure to come back to talk about my research, what I did in the past 3 years after I left here. Make sure that I keep the momentum I built up here at Stewart and still doing like interesting work. I think this project has a lot of collaborations with Laird and with like a phone here at Stewart, and I think it has a great synergy with the project people here has been doing. So I think let's get things started. I probably guess some of you or most of you have been like exhausted in the past few weeks from the JWST stuff, and so I'll have like a lot of pretty pictures, so keep us keep the talk lovely and interesting. So hopefully that works out. Yeah. So for today's talk, I will just start with some introduction of the latest progress of studying planet formation, especially direct characterization of protoplanets. A lot of this are thanks to like the ground-based development in the past few years, like the high angular resolution observations done by like ALMA and Sphere and GPI. Those are helping us to understand a lot of like what's the earliest stage of planet formation. And then I will start to talk about like our work in terms of like developing Hubble Space Telescope into a planet discovery and their characterization machine, so that we can use Hubble to image planets in the wavelengths that the ground-based observations are struggling with. And I think then I'll move on to like the core part of the talk. I'll talk about like one project I've been leading in using Hubble to look for H-alpha emitting planets that reside in the gaps of the transition disks, and share some the earliest result from this project. So this basically includes some like how do we do it, enabling high contrast imaging with Hubble. We'll talk about the ongoing search, and I will talk about like the detailed characterization in this project. Yeah, so let's get started. So I think thanks to ALMA and like the high angular resolution observations, we now have seen basically we can trace planet formation at pretty much every stage of the disk evolution. starting from like the very earliest days, like the class 0, class 1 disks, we have found like these substructures in these disks that may indicate an ongoing planet formation, or there's possibly pressure bumps that are creating those structures that can trigger planet formation. And as we move on to like the later evolution stage of the disks, the signatures and the disk substructures becomes more and more clear. I think Feng has done a lot of those work to review the disk substructures, that the gas spirals, those are possibly trace planet formation. And we go to transition disks, there has been already direct detected for planets, ongoing planet formation in those disks. And even we enter like the mature like planet system, the debris disk system. So the debris can help us to trace like the dynamically planet, giant planets in those systems. What about like the evidence of direct evidence of planets? In this protoplanetary disk, I think now the best evidence we have is from the movement of the gas in those disks. There's just a lot of extinction going on. It's really hard to see like direct emissions from planets in those like gaseous disks. But if we decrease the movement of the gas and see whether those gas has like a specific deviation from Kepler motion, we can find like a velocity kinks in those disks to trace planets. And that's provide us a very early on evidence of planets in those disks that are interacting with the disk. And then move to like the more clear version of the transition disk, the planets has been detected. This is one of the very famous example, PDS-70, which has occupied me and occupies a lot of people in the last couple of years to study it, try to characterize it in multiple ways, and use it as a laboratory for understanding how do planets form and how do planets interact with disks. And in debris disk systems, we have a lot of this. We have a few classic examples of direct imaging planets. For example, HR 8799 was also discovered in like a debris disk system. And so these are all like very interesting results, very pretty pictures. But I want to focus on this stage of the PDS-70 system for like a little bit, because it's currently, I think it provides like the best example for planet that has ongoing accretion. Tell us how do planet build up its mass, or tell us how do planet gain its materials from its surrounding environment. So this system was discovered back in 2018, and that was still in Stewart. And I think the initial discovery was done by Sphere using in the near infrared. And shortly after, my office mate, Kevin Wagner, used MAGIO data to look at the HALPHA emission from the system. So back then he sat right next to me in Daniel's office cubicle. So we were like next door neighbor. So this image was made right next to me, just like 3 feet away. And so the importance of this image is it shows the discovered planet PDS-70b in this direct H-alpha image has a huge H-alpha emission. So the H-alpha emission from the planets basically is much brighter than the actual H-alpha excess from the star. So that helps to reduce the brightness contrast between the planet and the star, help us to easily recognize the planet, and also show us this planet is experiencing ongoing accretion. And then Sebastian, which back then I think is in Netherlands, but then moved to Stewart. He took he used the VLT Muse instrument to look at it. I think it has higher spectral resolutions and look at this system also in the H-alpha emission. And he did not only see one planet, but like 2 H-alpha access in this system. So see like so basically this system has 2 planets that experiencing ongoing accretion. And that's very exciting. So give us a really good example to try to understand how the planet form. So I think the importance of this system is I would like to use this spectral energy distribution of PDS-70B represented. So you may like build up, try to make a case of one planet maybe is the most studied planet among all the more than 5,000 exoplanets. For example, you can say like WASP 39b, which has a lot of GWST data coming out in the past few months. You can say that's maybe one of the most studied ones. But I can make a case for PDS-70B and C to be one of the most studied one because I think its observed SED occupies the widest wavelength range among all the planets. So its range is all the way from like the UV, which we had a HST image for it, to like H-alpha, that we have ground-based HST and data for it, to like near infrared data, and all the way to like a millimeter observations from ALMA. At least for like PDS-70B, we have clear evidence of a circumplanetary disk that has been discovered by ALMA. So it goes all the way to like just over 1,000 angstrom to like millimeter wavelengths. And there's planned observation by HST trying to look for Lyman alpha emission from the planet, which I'm part of the program. I think the data is going to be taken in the next few months. This is going to be a very challenging program, trying to find the Lyman alpha access from the planet. And there is several, I think, planned GWST GTO programs trying to look for the Passion alpha, bracket alpha emission from the planets, as well as the mid-infrared characterization for the host star. So it just occupies pretty much the entire electromagnetic spectrum, and it will give us a lot of information to try to figure out like what these planets are doing. So just one interesting thing, I just want to play this image. This image is the press release image Space Telescope made for us for like one of our the HST characterization of this system. It looks kind of like a sci-fi or like too much. It's just too much stuff in it. But I think it's scientifically it's accurate. I think each element in this image is traceable from actual observations. For example, let's see this photosphere here, like the red photosphere is traced by like near-infrared observations, and we can use data to back it up. Circumplanetary disk, there is ALMA observation that show at least the PDS-70C had this disk, and the excess emission from the gas flow flowing onto the planets that triggers hydrogen H-alpha and like UV excess emission has been probed by HST and the ground-based observation. So yeah, even though it looks like sci-fi, but it's reality. I think it's a great picture to indicate how the planet formed, at least a giant planet formed. So let's see what we actually learned, like what progress has been made from like the case studies of PDS-70 system. So we learned that there is a planet disk interaction. We learned something about planet disk interaction. So if we Keihan-Bei did this like a hydrodynamic simulation of the system, put two planets in, use the observed mass accretion rate of the planet, try to simulate what the system will end up with. And this is the ALMA observation of the disk, and this is the simulated disk. And it shows that the accreting planet can actually really reproduce the observed structure of the giant gaps in the disk, because the planets can carve out this hollow region in the disk. And we now probe that there are, the planet has ongoing accretion, and there are multiple accretion fronts that can occur in this system. There are like accretion from the circumstellar disk onto the circumplanetary disk, and the circumplanetary disk can have like accretion onto the star. So this multiple accretion front create hydrogen create this hydrogen excess emission, and the excess emission help us to trace. We can use the excess emission to convert that into the kinematic energy of the accretion flow, and they trace like the accretion rate of the planet. And observationally, it also give us this nice tool for looking for planets. So if we plot the expected, like the spectral energy distribution of this protoplanets, we can see in the near infrared is pretty much occupied by its photosphere emission, although in this case it's sort of featureless. But in the optical and to the UV band, it starts to be mostly dominated by the excess emission due to the accretion, and the line emission can really reduce the contrast between the planet and the star and help us to better identify the planets. So this idea is not new. I think Laird has been invested in this idea quite a lot. He used like MAG-AO to looking for planets around like young stars. And so there has been like a lot of ground-based research to looking for planets in the gaps of transition disks. I think one of the most dedicated, I think gave us the most constrained surveys from the MAG-AO and I think ongoing MAG-AO-X observations that has the latest result is from Kate Flat 2022 paper. There has been more than like 10 stars surveyed. There is this very classic example of Nicholson 15b. There's HALPHA access from the giant planets, and there is Kevin's detection of PD70b's HALPHA emission from these, all coming from this survey. So people also used VLT to look for HALPHA emission, but so far use like the spheres ZIMPO mode in the optical band. So far there has not been planet detection reported. And then there is Sebastian's Muse observation. It gave us the two planets in PD70b, show us those planets are heavily accreting. But that's about it. There's the yield is there are exciting results, but we want more. They're not like every star we observe there is accreting planets. The yield is probably like 1 in 10 or even less than that. We want to figure out like if planets are not accreting, they're not bright in HALPHA, and why do we not see more than what we have here? So I think to explore the reason, Laird has a paper to build this model, try to figure out what kind of actual yield should we expect. So I think in this model, so basically the idea is just to put 3 planets in the gap, assuming that the transition disk gaps are carved out by like 3 planets in the orbital resonance of 1 to 2 to 4, and assuming that the accretion rate onto the planet scales with the accretion rate onto the star. And then let's see how many planets we can discover from our current instrument. So the result kind of looks like this. So this is the MAG-AO's 5 sigma contrast curve. So planets that are above this can be detected. And below this 5 sigma contrast curve, it basically is our detection limit. Below this, we cannot detect those planets. So for the system that has been surveyed from the ground-based telescopes, most of the systems are below this curve. So why do we look at those systems that are apparently not the best, sort of the best system or the most promising system for discovering planets? Is I think the most important reason is it's really hard to do optical AO from the ground. I think Laird and Sebastian can say a lot about it. It's just the HST is really hard to achieve a very high HST ratio. So we have
particularly on the faintest sources.
Yeah. So we have to observe pretty much the bright stars, and also like the the best optical AO system, the MAG-AO, is in the southern hemisphere. So we don't access to a lot of like the stars in the north, like in the Taurus stars, just is struggling to get those stars. But like HST, it doesn't have that problem. We can use HST to look at a faint star. It doesn't need an AO system. It can access to like stars in the northern hemisphere. So it actually, if we can make like high contrast imaging on HST work, we can make like optical high contrast imaging with HST. So we can use HST as a really good like a company tool to like the MAG-AO and other like AO systems that have been using on the ground-based telescopes. So then we come up with this idea. Let's see, like if we overplot the HST contrast curve we achieved from the PDS-70b observation and plot a lot of these fainter stars onto this graph, we start to see those systems becomes more promising. So this gave us the idea to let's launch the program to use HST to look at these stars and see if there are planets there. So that's the whole idea for our survey, to make make HST work as a high contrast imager, and then let's look at those stars. But HST is mostly like basically a general instrument. The instrument that we use here is called wide field camera 3. So it's a wide field camera. It's not made for it's not called a planet imaging camera. So it's kind of it's not optimized for looking at a narrow field to do high contrast imaging. Its pixel is really big. It's optimized for wide field observation. So it's not well sampled, and it's pretty challenging to do like a very precise like a PSF constructions and subtraction. So for the case we observe PDS-70b, we start to combine some of the most modern like imaging process techniques, try to put this into the HST observations and made it work for using HST to look for planets. So to show you how like challenging it is, I just here put like the image of the PDS-70 and use this small arrow to show like where PDS-70b is. It's just like a little bit more than 5 pixels away between the planets and the stars. So we really need to understand the PSF very well. So to do this, there's a pretty much like we combine a few techniques. I just give you a few, like a quick explanation here. So the techniques we made is a lot of them are inspired by like the last decades, like ground-based development. Like the angular differential imaging has been showed to be like a very effective way to construct a precise PSF and do this to model the point spread function and subtract the stellar emission from the image and review the signal of the planet. And I learned that from working with Daniel from this, like we do this to get the light curve of the planet. And I learned that we can actually apply angular differential imaging with HST and build this into our observing program. And it's also important to reconstruct the PSF to make the images like quiz sampled so that we don't lost information when we reconstruct the point spread function. So there is well documented algorithm but this has not been like really used in imaging planets with HST. But I applied these algorithms to our like observation PDS-70b and made it work. Make the PSF more than makes a PSF more than like quiz sample by doubling the sampling rate by combining like 4 images that are observed slightly different in their pointing by like a half a pixel, so that I can double basically the idea is make the pixels like half the size of the original pixel size and reconstruct a well-sampled PSF. And then there has been a whole suite of high contrast imaging algorithm that has been developed, like the CLIP algorithm for most optimized way to reconstruct the point spread function to for modeling the PSF observations in reducing the angular differential imaging tubes will preserve the signals and the most precise way to estimate the signal, the noise of the detector. Build everything in and then make it work. So we have this ultraviolet and H-alpha detection of the PDS-MTP in these two images. And this is the first ultraviolet image of any planets ever, I think. So we can use this to calculate the energy access from both the UV continuum and the H-alpha, and to do, I think, the most accurate estimate of how fast the planet accretes using this kind of bunch of algorithm. So one thing I want to add is after this, we have additional development of the algorithm. One UT undergraduate student working with me, Aniket Sanghi, he provided this new image processing method to basically collect all the H-alpha image that has been observed by HST over the past 10 years, or like more than 12 years since like Wide Field Camera 3 launched into space. So collect all the images and use those as reference point spec function and apply it to our observation PSMTP and use that to model the image of the star and subtract it from the star and review the signal from the planet. And this really showed that we can use reference star differential imaging to process the image with HST, and this really makes the observation a lot more efficient because angular differential imaging is challenging to schedule with Hubble. You cannot like just tell like Hubble rotate in this way. It's not how we control the telescope. We can break the telescope in that way, but we probably cannot achieve science in that way. But allow reference differential imaging with Hubble, we can make the observation a lot more efficient, and Aniket shows it works. And I think Aniket is applying to grad school in U of A. I hope he is ranked very top in the list. It's just really good. So yeah, that's it.
I think you'll have lots of options.
Yeah, I'm sure. Yeah, so just to summarize the first part of the talk is we show that the
Actually, just one quick Anklit's a paper. So if I remember reading it, it was a real tour de force of like being able to use HST without CLIP, without ADI, and just use reference imaging. But I thought, is it true that the signal to noise was just a little bit worse than what you were able to achieve in your paper?
Yeah. So the PSFs, like the PSF library, just not as good
as what you could just do with ADI.
Right.
Yeah. But it's close, and maybe that's really the highlight is you can get close.
The signal noise we achieved with ADI is like a 7, with like the reference like RDI like a 5 or a little bit after a 5, but it's just limited by the quality of the PSF.
Right, but that's based on, for the important part for the audience, it's based on PSFs of different stars.
Right.
Taken at different times, even years different, right? I guess. Yeah.
And I think it's also very important for JWST because for JWST it's even more difficult.
Yeah, it can barely move.
And I think from the early release science result, it shows the ADI probably has the worst result compared to like RDI. Like even use the model PSF. I think it's quite important for space telescopes in general. Just to summarize the first part is show that the gap transition disks are good targets to look for planets, and accreting planets are bright in H-alpha. So we enabled HST to do high contrast imaging that are not currently accessible from the ground. So we launched this H-alpha program to look for transition disk planets around the fainter and like a gapped systems. So we selected these systems. Laird did a lot of work on like helping selecting these systems so that we use the ALMA images of this system to try to select the best system that point HST at those systems to look for planets. So that's our idea, and the idea was approved by the HST tag, and we were able to performing it in the last year. So just give you a big picture of that's the 10 systems that we are looking at, and currently we get HST images of 8 out of the 10 systems. Actually, we got 1 additional observations of DM count in the last month, but I was occupied with the JWST proposals, haven't been able to look closely at this, but this, and we'll have one more image in I think in next month we'll complete the survey. And so basically you can see it's pretty. There's a lot of structures, and I think we can probably divide it into like 3 categories. Like one is there's these 2 adjunct, more like inclined system. We see this large scale scatter light features in the GM-OR and the PDS-99, and we also see like a jet feature here. And in some systems, we see this scatter light features that are basically placing the small dust in the disk. And there are a few like a clump, like a point-like source in the system. So in general, 3 categories. Just take a closer example of one of the large-scale structures. This is one of the famous like disk GM-OR is inclined, has these 2 gaps observed by ALMA, and we see it has a symmetry like a scattered disk features that show a kink. I had these pictures trying to understand what's going on, and still need some work to do to try to figure out what exactly this 3D pictures tell us about the disk structures and whether this trace like a planet formation in the disk. There's also this system, like 2 at least the scattering friend and the jets. So one thing I think it kind of bothers me is this 3D pictures, they kind of introduce like interference with identifying like a point source in these disks. Yeah. They try to think what's the best way to solve it. And then there is this system that is probably one of the best systems in our survey. It has this J1604 has this giant transition disk, and the giant hole. The size of the hole, angular size, is about 0.4 arc second. So it's very comfortably for HST to look for what is inside this hole. And we are very confident to detect that there is these 2 arcs that has been observed by ground-based observation before, that the trace like the small dust that are produced by the pressure bumps in the disk. And there is like this 2, like a fainter part of the disk that is also observed from the ground. I think that's the idea is there is the inner, very unresolved disk around the star that is blocking light from the star. So it's a shadow of the inner disk. And there is also a lot of stuff within. And if you count this, 1, 2, 3, 4, 7, 7 planets. I think Kato will kill me. Like, but I think the interesting part for this disk is a couple weeks ago, there's this paper looking at the 12CO motion using ALMA in this disk, and they compared the velocity map of the 12CO gas with the prediction from the Kepler motion. And they see this non-Keplerian features in the disk. And they discuss several mechanisms that maybe can create this. And the most promising idea is like a 2 to 3 Jupiter mass planets that are disturb the gas and create these velocity features. And the location of the planet, the giant planet's companion, they proposed is at the separation of about 0.2 to 0.4 arc second at the position angle of 280 degrees, which coincides with one of the bright source here. But I just cannot say like our observation provide like evidence or like either like for it or like against it. Like if I just look at the signal to noise map, basically compares the axis emission here versus the as mutually average the noise level. The signal noise is not there. It's not like a solid detection. However, if I just tweak the parameters that reconstruct the PSF, tweaks the region where I optimize the point spread function reconstruction, there is some sort of like a 3 sigma signal here. So this puzzles me, like which image should I trust? And I think this is like a classic kind of a problem that we have in high contrast imaging. How do you robustly identify like the point source in this really high angular resolution and high contrast regime? Just really proceed to like these images. There are like multiple these kind of clumps that looks promising. But they need like additional work to identify.
I think you go back to the previous slide. So, is there any model, forward modeling of the system? Because this, not the source, not the point like source, but the extended source next to the rim. That could be part of the HST of a planet there. That is, draining out the depth.
As far as I know, I don't think there are like the horseshoe idea has been explored by simulation. Sean, do you know?
Yes, there are some, not this one, but
Not
for
for-
general expressions. Yeah.
Right. For
You mean the outer ring or the?
I
this,
mean, you have this symmetry distribution of extended sources next to the ring, right? Then you mentioned there could be small dust grains.
you mean this ring?
Yeah, or the one that you're showing in the HALPHA, which is not a ring, but it's just two standard bright spots next to the ring, right? The one that you have the arrows pointed to.
Yeah, like this.
Yeah, the one at the top.
Yeah, I think this mostly. I think the idea is it's just like a circle of it's continuous circle of the small dot, but this two fainter region we don't see it because of the inner disk shadow. I think that's the mostly settled idea. I'm not aware of like the horseshoe.
What's the inclination of the system?
It's pretty much like 85, nearly like face out.
I mean, just to help us understand this, is the sphere image, is that like,
That's the total intensity.
yeah, I know. And so the shadows, is that what you're seeing there too? Those two little, so it does kind of look like a continuous ring, with like two little faint shots. Sometimes sphere actually does take very nice images, and that's a good example.
Yeah, this is a good paper. If you want to see like a nice disk image, this I think one of the.
Although, is it sphere or is it muse?
No, this is sphere.
That's sphere, okay.
Muse cannot do this.
Okay, yeah, because it's higher
We
resolution.
see those shadows more in other disk observations. There's lots of large disk programs in sphere. And there's also a couple disk observations where we actually see the shadow move on like on a month time scale.
I think
So it's
this
very clearly,
that's the time variability of the shadow.
Yeah. So it's definitely something orbiting close to the star and not the disk itself.
Yeah, so fascinating systems. Just to go back to this image, I think there are pretty much like two directions that we need to push forward in terms of identify the point source. One is like from the data processing point of view that we want to make sure like all these like point like source, they survive all the tests we do, like make sure they're robust, we tweak the whatever parameter we use to reconstruct the PSF, the point source has to be there. We change from using like the angular differential imaging PSF versus like a reference differential imaging PSF. This source has to be survive. And I think another kind of a direction is the spectra and the astrometry of the identified source has to make sense to be like a planet-like signal. So I want to discuss the second part a little bit more with this target, this AVR that has been discussed a bit in the last, I think, half year. So it starts with this paper that announced the discovery of a protoplanet, but I would call it a protoplanet candidate in this famous transition disk system, AD-OID, and it shows this blobs-like features. Is they identify this as a embedded protoplanet. This can be really like significant, like a discovery, because if this we like confirm that this is a planet, I think it's the first system that is a planet is embedded in a disk structure. It's surrounded by a disk materials. Really tells us how do this planet gathers all the materials around it and gathers its mass. I think the discovery paper also provides several lines of evidence I will go through next. But one thing I want to show is like it's included in our HALPHA survey, and we also see a point-like source, but it's not exactly point. It has these extended features. It's bigger than the point spread function of HST. And this image is firstly processed by Aniket, which I mentioned a couple slides ago. He looked at this image in February 2022, and after one day, I gave him the image. He sent me back this, and we were like, "Oh, this looks interesting." And we have this. We show, it has this features in the HALPHA. So in the original Curriel discovery paper, the author present several lines of evidence that this is actually a planet rather than like a blob in the disk. So one evidence they present is so if you measure the spectrum in other part of the disk, you get a spectrum that looks kind of like this. But if you measure the spectrum here, it has the bluer slope. So the spectrum are different. But the difference is like 2 to 3 sigmas at like 2 data points. And another line of evidence is they also take a polarized light image, which traces the scatter line from the disk, and the polarized light, we don't see excess flux here. So meaning that this cannot be, from their point of view, cannot be like a scatter light from a star. So it has to be self-luminous. So if there's a self-luminous concentrated light, it has to be a planet. And also there is optical motion shown in like multiple epochs of images. But I want to remind you, like, this is a disk of ADR. Has a lot of structures, just too complex, and the radiator transfer process just it takes a lot of effort to model. And I think we sort of like it's difficult to try to understand, like trying to identify whether the source we see here, access source, is really like a self-luminous or not, like whether the evidence presented so far is sufficient. So we want to see if our HALPHA image can lend actual evidence to support or against that this has to be like a protoplanet. So basically the HALPHA would give us like the evidence that if there is a concentrated mass at this position, it probably has to accrete materials around it. And this accreting material should provide this HALPHA access. And also if we go back to look at its spectrum, it's blue. It's weird. The planet spectrum should typically not this blue. So the green line I show here is 4,000 K black body. It's really hard to make a planet that hot. So the idea I think presented in the discovery paper is in order to make this object look so blue, it probably has like excess hydrogen emission in the Paschen continuum and the Balmer continuum to raise its continuum in the optical band to make it blue. So it sort of indicates that this has to accrete. So we took our HALPHA observation, compared with the continuum, and we see like access. But does this access tell us this is accreting planets? I think we need to take an extra step. So we compare the HALPHA access with the HALPHA emission from the star. And the star also have HALPHA emission. And it has well characterized the spectrum, this one is taken from the 2.7 meter on the McDonald telescope. And if we integrated that within the HST bandpass, we found the stellar one it's very consistent with our observed one from the supposed planet position. So we cannot tell that whether this is H alpha access from the planet or is it simply just the scatter light of its star, just to represent the stellar spectrum. If we compare like the spectrum between the ABOR-B and the PDS-70B, we found it looks just two different things. Like the PDS-70B has a red photospheric emission, like 1200 K black body, and a huge H alpha emission that is 1,000 times brighter than its continuum. But for ABOR-B, it's very blue, 4,000 K continuum almost. And like the H alpha axis is just a factor of like 1 to like 3 above its continuum. So if we summarize this evidence, I think we can't just use H alpha to justify this being a photoplanet. I think the question is still whether this is a very young photoplanet embedded in the disk, or it's like a dust cloud try to disguise as a planet. So last few minutes, want to present this ongoing experiment that we are doing with HST. We try to construct this light cycle experiment and tell whether the H alpha emission we see is from the planet or from the star using time domain information. So the idea is like this: we take a picture of the star, measure its H alpha emission, and we know that the star has variable H alpha emission on the scale of about like 10 to like 30%. And then because the light takes about 13 hours to travel from the star to the supposed planet position and reflect it to our telescope, we wait for like 13 hours to take another picture of the system. And this is like one example of our experiment. On January 7th, we take image of the star, get a sense of how bright the star is in H alpha, and wait for 13 hours. During the 13 hours, we have ongoing ground-based observations. Look at the star to understand how much the star varies during this period of time. This include like AAVSO, like so from amateur observations, amateur astronomers using McDonald, and also using like a telescope at Flagstaff, trying to understand how much the ABOR, the whole stars vary, is coordinated by Lauren Biddle. I think she is used to be undergrad here, and now she is a postdoc at our group. And we have this whole campaign to understand, try how much the star varies. And then 30 hours later,
go ahead. I have a question after this slide.
Yeah, take a picture of the supposed planets, and we have another detection of this. It's very high signal noise, help us to understand how bright this source is in H alpha. And we will repeat this experiment for like 5 epochs. So if the H alpha is self-luminous, it's from the source, they should be uncorrelated in this experiment. It should look like this. And but if it's reflecting from the whole star, it should be closely correlated. If the stars vary, the planet should vary in the same way. So we have our first epoch data taken, and the next epoch is next week, and the entire experiment will last for the entire year. And I think this will give us a very clear evidence of what this source is.
So there is a question from Andrea Isela. Andrea, would you like to speak up, or should I read?
Sure. Can you hear me?
Yeah.
Yeah. Okay. Hi. Yeah. No, my question was about the H alpha emission from ABOR-B. So, if this object is still very embedded in the disk, I wonder, how does the H alpha emission from the object itself escape? Because there should be material on top, and the optical depth of the dust at the H alpha wavelength is probably very, very high. So I think it's enough to have a little bit of dust to reabsorb all your H alpha emission. So can you comment on that?
I think the extinction is a big uncertainty here in this system. I think one possible evidence that this is not exactly extincted is it has this optical band detection from I think HST but we still have to figure out whether that's from like just the scatter light from the star or is escaping from the underlying source. So in the next few slides, we have like additional HST time to collect like it's optical to UV SED, trying to compare that to the star to figure out whether its optical emission is from the star. So it could be entirely that the optical emission cannot like escape, like it's purely extincted. That's a big problem I'm trying to figure out, but I think you're right that the extinction is uncertain.
And there's another question from Christoph Mordassini. Would you like to ask a question? You can speak up. Or I'll read it. Okay, so would a spectrally resolved H-alpha line allow to distinguish star and planet? Disentangle, yeah.
So if we see like a velocity difference between the planet and the star, that'd be great. So far we haven't got like a spectral result information. I don't know if like MAGIO-X could.
Well, it's Muse. That's what Sebastian.
Can Muse do that?
And
resolution wise?
The main problem with AB Auriga is that it's so low on the horizon. So even in the best conditions, you will get very perhaps AO performance. You will get like 100 milliarc seconds or 150 milliarc seconds full width F max. So you will not be able to resolve it.
So in 2 days, Lauren is going to use OSIRIS to look at the Passion beta line of AB Auriga B and see if we can use spectral resolved information to differentiate those two. So I think that's the exact idea of the proposal. Yeah, I think we are about time. So I have a few more slides, but I think I want to end the talk here. I pretty much gave like the entirety of my work in the last year or so. So basically, let's see. If I sum up, I think the one thing I want to emphasize in this talk is the space telescope, a indispensable like instrument help us to directly characterize protoplanets. And in the last few years, we have make it work to use HST to do high contrast imaging in optical and UV band, and that's helpful for like I think that combined with like ground-based telescopes that are going to really push forward our understanding of the protoplanets and how do they form. So we have launched a suite of interesting programs like Light Echo. Another is like the UV to optical band SED characterization of AB or B. That's going to happen in next, I think next or basically in 2 weeks we'll get the data. We'll tell like what is the UV to optical SED will look like. And I think the future is going to be a lot more interesting. We have a whole suite of telescopes like GWST, like GMT is going to image a lot more like protoplanets and help us to understand how the planet forms. So yeah, that's it. Thank you so much.
I see right away we have a question online from Robin. Would you like to unmute?
Sure. Hi, Yifan, can you hear me?
Yeah.
Great talk. So I have another question on AB Auriga B, sort of a follow-up to Andrea's question. So H-alpha, those H-alpha photons, they kind of have to come from deep in the potential well. So by any means, there will be a point source. So it's different from the infrared case, which you can imagine you have an envelope kind of thing, like a Dyson sphere around the planet. You can process those infrared photons. So the explanation you could make the infrared emission extended, not a point source. So I think you mentioned in your H-alpha observation, you also see the H-alpha quote unquote detection is not exactly a point source. So is there any explanation if it is really coming from a planet? So how do you make the H-alpha thing not a point source?
It's I guess it's hard. I need to think about it. Like the accretion front has to be fairly small. So it's so I think that the case is whether the H alpha we see is a mix of scatter light or is a scatter light of it's a mix of scatter light and emission from the planet, or is it purely scatter light. So I think the new experiment will tell us that. But the extended emission has to come. Some of them has to come from like a scatter light from the host star.
I see. So from the source being extended, you know, at least not all the H alpha you see is from the planet then.
Right.
Okay, thanks.
Yeah. So one of your programs is to look at the Lyman alpha emission, or trying to go to really.
Yeah. So I'm part of the program, not the lead.
I was just wondering if is it really possible to do that with HST, because you're looking through like the Earth's H alpha Lyman background. I mean, I've looked at HST data myself to see what the sensitivity limits are, and they're very close to what's the expected accretion, at least the line flux would be. So,
I'd be interested to see like what we are going to find. I'm not 100% confident. I think the argument for using Lyman alpha is if you trust those accretion shock model, the Lyman alpha is going to be way much brighter than H alpha. That helps the signal noise. The difficult part is, yeah, as you described, like there's going to be like a lot more interstellar extinction and making the signal difficult to detect. So yeah, let's see what the image will tell us.
Other people have questions?
Well, I guess, I mean, actually, I'm fairly convinced this thing of Thane's is just, he's discovered a clump in the disk. But anyways, but I mean, I guess the other thing you could do is you could look at the at AVOR, I guess, in the in the UV as well, to see if there's, because the disk probably wouldn't have a huge amount of UV, like from reflected light from the central star. If you saw a strong UV source there, that would be exciting, I guess. But I don't know if so
that's my toy model.
Yeah.
The pink line suggests if it's accreting, it should have UV access, and so the planned observation should be able to tell us if we had a huge UV access like we showed here.
Yeah.
Like we observe here, it should suggest it's a planet. But if there's nothing observed here, like if we observe like a sort of like a lukewarm like UV flux, is probably shows it's reflected from the host star. So these observations will take in next 2 weeks.
Okay, that's awesome. That's a perfect answer.
Well, what about the variabilities? So that, for instance, the accretion for the stars vary, right? But in this case, how much variability do you expect?
From the host star, or from...
I mean, from the planet and from both sides, actually.
We don't know. We want to figure it out with PDS-70B, try to characterize its variability. I think Sebastian also has ground based
monitoring.
It's like probably not too much from PDS-70B so far. But I think for the planet, we have no idea.
Yeah, it's possible different planets will be different variabilities. It's like Pitari stars, right? Each one is.
The most annoying thing might be the variability of what due to accretion onto the star. I think it should be taken care of.
I also had one question about this. Isn't the UV, like the shorter wavelengths, also more affected by extinction?
Yeah. So we try to. So our argument is like use multiple band. We can combine with like a previous data. We can at least have some constraint, like to fit the extinction model to try to see if it's like high extinction UV access or it's like low extinction no UV access. I think the multiple data point helps with that.
Yeah, top of the hour. So, yep, there are no more questions. Let's thank Yifan again. We're still stuck.
I'm stopping recording.